All right, related rates example number 3. One of the most classic, if I could speak, related rates problems are the shadow problems. So I'm going to go through this problem and then I'm going to relate it to the other kind of shadow problem you might get. Okay, so we have a man who is 6 feet tall, walking at a rate of 5 feet per second away from a light that is 15 feet above the ground. Okay, so we got to draw this. Okay, so I have a light. So light is up here. Okay. And a man, which I'm still just going to use a line. So the way these things work is the light will hit the man and continue to make a triangle, a straight line. And let's see if I can kind of label this with a line. I'm going to try anyways. This part here that I've drawn in red, this is the shadow. That is the geometry of these problems. Okay, the shadow is always in this behind, obviously, after the light is on one side, the shadow's on the other. And it always makes this sort of straight line from the top of the light to hit the thing, top of the thing, making the shadow to the tip of the shadow. That's going to be a straight line. Okay. Obviously, if this person is closer, right, then that's a steeper line and a smaller shadow. Okay, so that is the geometry. Let's go back and read the rest of the problem. So 15-foot light, 6-foot man, and he's walking at a rate of 5 feet away, okay, from this light, which we'll talk about how to fill that in just a minute. When he is 10 feet from the base of the light, at what rate is the tip of his shadow moving? Okay, so there are a couple ways to do this. Sometimes people want to label the shadow as one variable, like an X or a Y, and this distance from the man to the light as an X or a Y. But I have to take into account what I'm being asked. The tip of the shadow moving means this point right here, not the length of this whole thing. It did not say the length of the shadow. If it said the length of the shadow, then we would want to label this as X or Y because we want to know how this is changing. But if it's the tip of the shadow, all I'm interested in is how this point is changing, which means I need to measure it against a fixed point. So when these problems say tip of the shadow, then you want to label the entire distance from the light to the end of the shadow as one variable. And that is going to be the thing that you are looking for, is the dy dt. Okay. That will measure just how this is moving, not how this whole thing is changing. Does that make sense? I really hope so. So if this problem had said, at what rate is the length of his shadow changing, we would have made y just be this. Okay. Now, let's look at what we want or what we know. We know that he's walking 5 feet away from the light. And we also are given these 10 feet away from the light. So it seems like the other thing we know about is this distance between the man and the light. So we will call that X. That means that we know that dx dt is it positive or negative 5? If he's walking away from the light, then the X is getting bigger, so it would be positive. And we want to know all of these things at the moment when he is 10 feet away, so that would be when X is 10. Okay, once again, take a second to pause the video if that's going to help you just spend a little bit more time digesting the diagram. Now, to come up with an equation to relate these two things, we are going to use similar triangles. So you will see that we have, this is a right angle, as is this. We have a large right triangle and a small right triangle. And these two triangles are similar because they both have a 90-degree angle and they share this angle, which means that these two angles must also be equal. That's what makes triangles similar. If you also remember, when you have similar triangles, the sides are proportional. So like the base is to the base as the height is to the height. And that's exactly what we're going to use. So to set up our equation that relates x and y, we're going to use the similar triangle ratios. You can set them up however you want. You can do small triangle to small triangle equals big triangle to big triangle, as long as you keep the sides in the same order. Or you can do like height to height and equals height to height. It's up to you. Okay. So I'm just going to do, let's say 6 is to 15. So I'm doing the height of the small one over the height of the big one. So that will equal the base of the small one. The base of the small one is here. It's the length of the shadow. I don't have that directly labeled, so I'm going to have to write it as y minus x, right? And then over the base of the large one, which is y. Okay, so here is an equation that relates x and y, the two things that, one that we know about, one that we want. You would absolutely be silly to try to take a derivative with it in this form. I would definitely advise you to simplify this first, and in fact, you can solve for y. Right, I've got 15x equals 9y, so y equals 15 over 9x, which is divided by 3. I would way rather take the derivative of this equation than this one. Right? So I've been trying to say this all along. Simplifying really does exactly that. It makes your life easier. So once we simplified, we're going to go ahead and take the derivative of both sides. That's an x. Sorry, my x's have been looking a little bit like y's. Of both sides. And then we'll substitute in the thing we know. We know that dy dt is, no, we know that dx dt, sorry, is 5. So that gives us 25 over 3. What is that in feet per second? You'll notice we didn't even use the x equals 10. It didn't come out when we took the derivative since these were linear. The x did not come into the derivative. So it really didn't matter how far away the man is from the light. The tip of his shadow, if he's walking at 5 feet per second, the tip of his shadow will always be changing at this rate, no matter how far away he is. It's an interesting piece of information to note.